let's get started with the presentations. First up, we have Hannes Albers from the Mechanical Engineering Department. So let's welcome him, and he's going to talk on tackling climate change with the new carbon capture technology.
One of the biggest challenges humanity is facing this centenary is climate change mitigation. In fact, we are already on track to exceed 1.5 degrees global warming. Therefore, carbon capture is going to play a huge role for us. Carbon capture is a technology where you actively remove CO2 from the atmosphere and store it underground. This technology is a chemical reaction and is based on a chemical material that can be compared with a sponge. In the first phase, you expose the sponge to the atmosphere and absorb the CO2. In the second phase, you expel the sponge and capture the released CO2 where you store it afterwards. This second phase requires a lot of energy in the form of heat. And this is the biggest challenge that industry is currently facing. In fact, the temperatures at which this reaction is running currently go up to 900 degrees, which on one hand is a lot of energy that is currently sourced from the grid, and on the other hand is very harsh for the chemical material. So it's not very sustainable, but also leads to very high cost. In my research group, we try to make carbon capture more sustainable and more energy efficient. In my research, I developed a coating method. I developed a material composite called polystyrene metal organic framework, and this material is able to release the CO2 already at 70 degrees Celsius. I was able, through a developed coating method, to integrate this material into an actual system. So I developed a method to coat this material on porous metal foam and brought that foam in physical contact of the backside of a solar panel. In fact, solar panels not only generate electricity, but most of the solar energy is being converted into heat and currently just dissipates. So this system design uses the waste heat of solar panels and is therefore fully independent on the grid. So my coating method also allowed me to do accelerated aging tests to demonstrate how long this material will last. And through this accelerated aging test, I was able to demonstrate a stable material up to 6 years. We target a lifetime of 25 years, but this is still work in progress. This patented technology is very scalable. On one hand, because it doesn't rely on the grid. On the other hand, because of its optimized system design. So scaling will not be a problem. So what are the next steps? I'm currently planning a 30-day outdoor experiment here on the roof at BU to demonstrate the material stability under real conditions. So if you're curious to see this in operation, please reach out.